Welcome back to Practical PyTorch. Last time you learned to read the 3 errors that cost the most time. Now the payoff, how a trained model survives the process that made it. This is save, load, and use a model. You trained a model and the loss came down. But the moment the process ends, those weights are gone, unless you save them to a file you can load back later. The thing you save is the state dict, a plain dict of parameter named to tensor. Write it with torch.save, read it back with torch.load, and copy it into a fresh model with load state dict. Then switch to eval and predict, even on a single new sample. This video has 4 parts. First, the state dict, a plain dict of name to tensor. Second, save it to a file with torch.save, the dict, not the object. Third, load it into a fresh model with load state dict, and use map location to pick the device. And fourth, use it. Call eval, then predict on one sample. First, the state dict itself, the one object that holds every weight your training learned. Ask the model you built for its state dict. This is the same NN, sequential from the model you built. A linear, array.lu, a linear. One line, SD equals model.stateDict. It hands back every learnable weight keyed by name, plus any registered buffers like batch norms running stats. It is not a copy of the model. It is the model's parameters gathered into a dict. Print it and it is exactly what it says. 4 entries. First, 0 weight, shape 128 by 784. The 0 is the layer's position in the sequential. Second, 0 bias, shape 128, the same first layer's bias. Third, 2 weight, shape 10 by 128. That is layer 2. The array.lu at index 1 has no weights, so it is not here. And fourth, 2 bias, shape 10. A state dict can also carry registered buffers like a batch norm layers running stats. This small model has none, so its state dict is just these 4 tensors. It is a plain Python dict. That plainness is what makes it easy to save. Second, save that dict to a file, and the one habit that keeps a model portable. Torch.save writes the dict to a file. One call, torch.save model.stateDict, then the path model pt. Give it the state dict, not the model. It serializes the dict of tensors to one file. Here, about 400 KB on disk, one file that holds all the model's weights. Torch.load will read that same file back into a dict later. The file stays on disk after the program ends. You can write torch.save of model the whole object. Don't. The portable line is the second one, save model.stateDict. Saving the object feels convenient. One call, no rebuilding. But modern torch.load refuses to unpickle a whole model by default. It uses weights only true for safety. So torch.save of model will not even load. Force it open with weights only false, and the pickle still hardcodes your model's class by its import path. So if that class lives in your own file, moving or renaming the file breaks the load. The state dict avoids both. It is only tensors, loaded into any code that rebuilds the same architecture. Third, load those weights into a fresh model, built from scratch in a new process. Later, a new script, a new process. You build the same architecture from scratch, the same linear, array.lu linear. Its weights start random, so it does not match the trained one yet. The fresh model already has real parameters, same shapes, random values. Load state dict will overwrite those in place. It does not create them, which is why the architecture must exist first. This is why the state dict is portable. The file holds no class, just named tensors. You rebuild the same architecture in code, then pour the weights in. Read the file and copy each tensor into the fresh model. One line, fresh.load state dict of torch.load model, PT. Torch.load reads the file to a dict. Load state dict matches each name and writes the tensor into the model's matching parameter. Now the fresh model holds the identical saved state. The proof is 2 lines. Fed the same input, the fresh and trained models differed by 0.749 before the load, and by exactly 0 after. Same weights, same answers. The weights were saved on one device. Loading them onto another, say a GPU file onto a CPU machine, is one keyword, maplocation. Pass maplocation equals CPU into torch.load. A saved tensor remembers the device it lived on. Load it on a different machine and PyTorch tries to recreate that device. So a model trained on a GPU can fail to load on a laptop. Maplocation overrides that. It remaps every tensor as it loads onto the CPU or a device you choose. That is the tool from the device lesson, applied at load time. And fourth, use it. Switch to eval mode, then predict on one sample. Before you predict, flip the model to evaluation mode. One call, fresh.eval. This is the same switch from the validation lesson. Loading the weights is not enough. A model fresh off load state dict is in training mode by default. Eval puts layers like dropout and batch norm into their measuring behavior. Set it before any inference, so your prediction is the model at rest, not the noisier training version. Our small model has no dropout, but the habit is not optional in real ones. A single example is shape 784. The model trained on batches, shaped in by 784, so we add a matching batch dimension with unsqueeze 0. Now 784 becomes 1 by 784, a batch of 1. The output will be 1 by 10, so argmax over dimension 1 has an axis to read. Run it under no grad and the logits come out shape 1 by 10. Argmax over dimension 1 picks the largest of the 10 scores. That gives a one-element tensor, and item turns it into a plain number. Here, class 7. No softmax needed to pick a label. Let's bring it together. The state dict is a plain dict of name to tensor. Every learnable weight plus buffers like batch norms running stats. Save it with torch.save of model.state dict and a path. The dict, never the pickled object. Rebuild the same architecture, then load state dict of torch.load. Map location picks the device. And call eval, then predict. One sample needs unsqueeze 0 to add the batch dimension. One check before we go. You save the whole model object with torch.save of model, not the state dict. What happens when you torch.load it back? Pause and predict. It fails. Modern torch.load defaults to weights only true and refuses to unpickle a whole model object because running arbitrary pickled code is unsafe. You would have to pass weights only false and trust the file. Even then, the pickle hardcodes your model's class by its import path. So if you wrote that class yourself, moving or renaming its file breaks the load. The state dict sidesteps both. It is just named tensors. Save the state dict. You can now train a model, keep it, and run it on new data. Next, everything in this playlist in one file on real images. The next lesson is the project, Fashion MNISD classifier, data, a data loader, a model, a loss, an optimizer, the training loop, and saving the result, all assembled end to end on a real dataset. See you there.